a paper called The Surprising Effectiveness of Linear Unsupervised Image-to-Image Translation. Their paper proposes a novel way to transform images in an unsupervised setting that runs many, many times faster than CycleGAN. Unlike CycleGAN, this algorithm, which is able to do image colorization, super resolution, and inpainting, all unsupervised with no pairs, was able to run and train in 15 seconds. First, we're going to introduce how LinM2M works, which is the name of the algorithm, and then we're going to analyze where it falls short, and then we're going to talk about what we're doing trying to improve it. We don't have final results yet, but this presentation will talk about our motivations. So how does LinM2M work? Basically, it takes a hard problem, transforming one image domain to another, and turns it into an easier problem, transforming one point cloud into another. And it uses a linear transformation called Q. Q is a rotation matrix because it's orthonormal, and we approximate the embeddings of image domain B, aka could be color images, with the embeddings of domain A, aka could be grayscale images. And we're talking about the PCA embeddings of each one of these domains. We multiply it by Q, and that gives us the other domain. And then we can unpack those principal components back into regular images again, and that's how we get our results. So how do we get this value, Q? Q is a rotation matrix that matches two unsupervised point clouds together. We don't have labels, we don't know which point belongs to which. So we have to use some kind of unsupervised algorithm. One that should come to mind because you took computer vision inside Stony Brook is iterative closest point algorithm. This is nice, and we're trying to find an orthonormal rotation matrix that will transform one set of points to another in PCA space. But there's a problem. It gets stuck in local minima. The authors try to mitigate this problem by finding a good initialization. First, they try to match up all the eigenvalues of the two distributions. This works fine and all, but there's actually a problem with it, which is that this eigenvalue matching looks just about the same to a computer as this. When you flipped it 180 degrees, it can't tell. The magnitudes are the same. So what they try to do is find a way to figure out the right way to flip these. First, we're going to show an example to give you a better intuition of what these eigenvalues look like and why they need to be flipped correctly. So here's an example where we're trying to translate grayscale images to color images. In an analysis that we've done, we found out that these eigenvalues actually look really, really similar. In fact, they might even look the same if you don't look closely. These have slight amounts of color, whereas these are completely black and white. And these are both, by the way, from mutually exclusive image domains, which is surprising because these eigenvalues look surprisingly similar. This is why we're able to translate from one domain to another, and as it turns out, Q is usually close to the identity matrix, which makes sense considering how close these components are to each other. However, there's a problem. You may see that some of these look inverted. Remember, gray is 0, black is negative, and white is positive. When you see these inverted, it means we're talking about the same problem when we're trying to match these eigenvalues, how sometimes it's flipped, and then we get a bad initialization for iterative closest point, and that's probably one of the causes for why they have more error than they should. The way that they try to solve this problem is by taking the skew of all the activations of the components and trying to, whichever one has a negative skew, they flip the component, because as it turns out, the components in these two domains have similar distributions. And even though the sign of these principal components may be arbitrary, the distributions are not, and by using the skew, we can figure out whether or not we should flip one of these principal components. However, it only works most of the time, it doesn't work all of the time, especially when the distributions are highly symmetrical like this. When this happens, you'll notice that it didn't decide to flip it, and even though, because this is the third principal component number 2 starting at 0, you'll see that this is actually flipped, even after it's been adjusted. So this is before, after. You can see that this looks more similar to this. The second component looks better after the adjustment, but the first component didn't change. But the third component didn't change, because this distribution was too similar. So our attempts to improve this algorithm will involve trying to find a better value of Q. One of them will be, perhaps, trying to randomly flip the columns of Q, which, by the way, is equivalent to trying to flipping one of the principal components. If we flip one of the columns of Q, it's the same as flipping one of these. And we could keep trying to flip them and see which ones give lower error. There's a problem, though. We can't measure the error of our results directly, because to get mean squared error between images, we would have to have paired data, which we don't by definition because this is an unpaired algorithm. So how can we measure error? Well, recall that what we're really trying to do is match two point clouds together, and so we can measure how well these point clouds match using the Wasserstein distance. This is something that they didn't try to do, and I suspect that it could probably improve the error by a lot. In a greedy manner, I propose flipping all the columns of Q to decrease the domain distances in the PCA. A second proposal that we'll try to use to improve Q, if the first one doesn't work, is that we're going to try using a generator and discriminator setup. Remember how this algorithm tries to mimic CycleGAN? Well, how could we get error? We could get error from discriminators. And so we're going to have two discriminators that will be battling Q. We're going to try to adjust Q. Q will be the generator, essentially, and we're trying to use Q to fool two discriminators. These discriminators will be weak enough that they can learn to Q and not destroy the gradient. And the third thing that we would try to do is learning M to M on patches of images. I don't think we have time to go over that in this presentation, but the idea is essentially that we would run the M to M algorithm on small areas of an image. There's theoretical justification for why this would work, but for the sake of time in this presentation, I'm not going to go over it. Lou, who's also on my team, will be talking about her results for trying to create a baseline.
Besides the analysis Ren has talked about, we have replicated baselines in the paper. Our results show that performance on paired images is better than non-matching pairs. This is consistent with the paper results. Our future work will focus on improving these numbers using our proposed methods, and we are writing these codes. Any questions about our project?
And that's the end of our presentation, which hopefully didn't go over 4 minutes, but we'll find out. Thank you for watching.